So for this video we're going to look at bubble sort. Last time we made a sort template, and we're just going to duplicate that template and call this bubble.py. And because we have this nice template, all we really have to do is in my sort, all we have to do is modify this function and implement bubble sort. And everything else will just run for us. All right, it'll compare the lists, tell us if the sort succeeded, tell us how much work it took, all of that good stuff. All right. So first of all, bubble sort, how does that work? Well, there's lots of different websites that will show you what bubble sort is. There's a good one here on Tutorials Point. And bubble sort is a simple sorting algorithm. The basic concept here is you start at the beginning of the list and you swap items if they're out of order. So for example, 14 and 33, they're in order, so you don't need to swap. But then you go to the next two elements. Is 33 and 27, are those out of order? Yes. So then you swap them. Then you go to the next two elements. And so 32, or 33 would be over here now. So 33 and 35, are those in order? Yes. Then you go to the next two elements. 35 and 10, are they in order? No. And then you'd swap those. So you'd have 35 here at the end. The point being is at the end of one iteration, the highest number will have bubbled up to the top. Okay, you see how that works? Because whenever you have a number that is out of order, so this 33 for example, we swap these two. And now when we compare the next two elements, this one is in the mix of the two that we're comparing. Right? So the largest element will always bubble up. So for example, if we had 99 down here instead of 14, 99, we would swap these two, and then it would be 99 here. We'd swap those two, it'd be 99, swap, 99, and so it bubbles all the way to the top. So in this example, it shows you here, compare those two, they do not need to swap. Compare these two, now they do need to swap, right? So then we swap them. Right? Now we compare the next two elements, right? The 33 and the 35, those are already in order. Then we compare the 35 and the 10, and those need to swap, so we swap them. Okay. Now at this point, we've gone all the way through the list, and we have one item here that should be the highest element in our list. Right? So at that point, we basically just need to do a bubble sort on the smaller list, this list here, okay, because this one is going to be the highest element. So then when we get done iterating through these items, right, the highest number from this list will end up here. And as you see, we compare 14 and 27, are those in order? Yes. 27 and 33, are those in order? Yes. 33 and 10, are they in order? No. So we swap them, and we end up with 33 and 10 here. Right? Then we go down with this smaller list, right? 14 and 23, or 14 and 27, are those in order? Yes. 27 and 10, no. So we swap. And then the last thing we have to do is compare these two. And then do we need to swap them, right? And by the time you finish, you now have a complete sorted list. All right? So let's see if we can do this in Python. All right. So in our sorted list, or our sorting algorithm, my sort, what we're going to implement is bubble sort. So you see, there's going to be some aspect of multiple loops, right? The first time through the loop, we have to go through each element in the list, right? And that's going to be one loop. That's a for loop. But we have to do that multiple times. So for example, for 5 elements here, we have to iterate through the items in the list once the first time, and then again second time, and but after that second time we'll have 2 items locked in. Then we have to go through the list again the third time, and then a 4th time. Okay, so for 5 elements we needed to go through the list 4 different times. Okay, so we can make that with the for loop. We can get that concept for I in range. And we had 5 elements in our list. So that's the length of our list, is the length of unsorted. Okay. So we had to go through one less than the number of elements in our list. Right? There are 5 elements in this list, and we had to go through 4 different loops, iterating through the list 4 different times. So that's going to be the length of our list minus 1. Right? So this outer loop is going to run 4 times, if assuming our unsorted list has 5 elements, which that's what we're going to assume when we first run this thing. Okay, so each time through this list, the outer loop tells us how many times we're going to iterate through our list. All right, the inner loop, we're going to have another loop. This is going to be for j in range, and we'll have to figure that out. Okay, so j goes from 0, and we want to compare that with another element. So if this is index 0, j would be 0, and then we need to add 1 to that to get another index. We'll call that k. So j and k, we're going to be comparing j and k. And then, so in this loop, again, we haven't finished this range yet. We don't necessarily know what we want to put here yet. But in here, we're going to say k is equal to j plus 1. Okay, so that just means if j is 0, index 0, then k is 1 more than that. And that makes sense because we're always going to be comparing with the item 1 ahead in the list, right? So we're always going to be comparing the item at index j with the item at index k. So if this is j, then that means the item at index k is here, right? And so on and so on. Okay, so we're going to have that idea. And we basically are going to want to compare these 2 items. So we're going to say, actually, instead of unsorted here, let's just make this our sorted list. Right? So we'll pretend unsorted isn't here anymore. And we're only going to use the sorted list. It would have worked out the same, but just so we use sorted everywhere, just so it's clear. Okay. So again, we still haven't set this range. We're going to get back to that in a minute. But here, if we're inside of this loop, we're going to want to compare if the item in our sorted list at j is greater than the item in our sorted list at k. That means they're out of order. So j is the item before and k is the item after, right? So j is always to the left of k. So if this item is bigger than this item, that means they're out of order, so we're going to want to swap. And we created this swap function up here. Okay, so how do we swap? Swap, we pass in the list, sorted, and then we pass in the 2 indices that we want to swap. We want to swap j and k. Okay, so if they're out of order, swap them. If not, just continue. All right, so this is most of the sort. We are missing this range here, though. Okay, so this loop, the outer loop, we know has to go 4 times if our list is 5. It has to go 1 less than the number of elements in our list. All right, and let's take a look here. J, this inner loop, is basically iterating. It has to iterate. J starts out at 0. It's going to compare with k. So there's 1 comparison. Then it'll increment, 2 comparisons, increment, 3 comparisons, increment, 4 comparisons. But it can't go more than that because then k would be out of bounds. Okay, so the first time through the loop, it also has to be the length of the list minus 1. Right? But then after the first time through the loop, the second time through, there's fewer comparisons it needs to make. It compares here once, compares here twice, and then 3 times instead of 4. And then the next time through, once, twice. And then the next time through, just once. Okay, so each successive time, so after each one of these loops, these outer loops, there's 1 less number of items in this list, this inner loop that we need to do. Okay? So basically for every one of these, first time through the loop, we need to subtract that from the maximum iterations of our inner loop. All right, so I starts out at 0, and for j in range, and it's going to be the length of our sorted list, but we're going to subtract, and we're basically wanting to subtract however many times we've gone through this outer loop already. Well, luckily we're keeping track of that here in a variable. All right, so the first time through the list, through this loop, right, this should be the length of the sorted list minus 1, just like up here. It's 4 items, because we looked and we saw that it goes through 1 comparison, 2 comparisons, 3 comparisons, and 4 comparisons. All right, so length of the sorted list minus 1. But then if we've gone through this loop, we want to subtract the number of times we've gone through the loop, that outer loop. So we haven't gone through it any times. The first time, I is 0. Right? So 0, this is going to be 0. The length of the list, this is going to be the range of 4. So that's going to be 0, 1, 2, 3. So I is 0 the first time through the loop, and then it's 1. So the second time we go through this for loop, this is going to be a 1, which means this range is going to be 1 item smaller. The next time we go through this outer loop, I will be 2. That means this range will be 2 items smaller. Next time 3. Okay, so we're using this value in our for loop to affect the length of the list of this nested for loop. Okay, so we can save that, and we'll see each time through the list k is going to be 1 more than j. We'll compare the items at j and k, and if the item at j is bigger than the item at k, we swap. Alright, so let's try this with 14, 33, 27, 35, and 10. Alright. So we're going to call bubble with 14, 33, 27, 35, and 10. There we go. So unsorted, we have a sorted list, 10, 14, 25, 27, 33. Python sorted, the same thing. Sort succeeded. The list of length 5 required 0 units of work. So we didn't add our work yet, right? And then the time complexity of the sort algorithm, right? And that's just the generic one we had from our template. So we need to fix those 2 items there. Before we get to that, though, I want to show you something about this structure, this for loop structure. Okay, so if down here I'm going to make a list, li equals a, b, c, d, and e. Okay, for I in range, length of list. This is going to run, the length of this list is 5. Range, length of list is going to create a list of 5 elements, 0 through 4. And then I is going to become each one of those items. Print I. Okay, so I'm going to run this again. And here, down here, 0, 1, 2, 3, 4. Now if I have a nested loop in here for j in range, length of li. And we're going to print out I and then j. Now here, how many items are we going to print out? Well, this outer loop is going to run 5 times. This inner loop is going to run 5 times. So this is multiplication, 5 times 5. All right, if we run this again, we see there should be 25. There's 5 that start with 0, There's 5 that start with the 1, 5 that start with the 2, 5 that start with the 3, and 5 that start with the 4. Right? So this is if we keep both the lists at the same value. The difference up here is each of those nested items was 1 less than the larger list. Okay, so down here, that's like saying range of length Li, but we're going to subtract I. Okay, so the first time through the list, I is 0. Okay, so the first time through the list, we're not doing anything. We're not subtracting anything. So this inner loop will run 5 times. Second time through this loop, I is 1, which means the inner loop, we're going to subtract 1. So there should only be 4 of these instead of 5. Next time, this will be 2. So there'll be only 3 of these. Okay, so this is a common way to manipulate nested for loops. All right, so let's just run this real quick and we'll see how many items we have. So here we still have 5 with the 0 in the front, but we only have 4 with the 1 in the front, and we only have 3 with the 2 in the front, 2 with the 3, and 1 with the 4. Okay, that's the pattern that we saw was happening here in bubble sort. We iterated through the list once, and then our next list is 1 item smaller. We iterate through all of that, and we get 2 of the top elements, and our list to be sorted is smaller. Iterate through that, we've got 3 elements sorted, and our list to be sorted still is smaller, right? So that's kind of the way you have to think about this stuff. All right, so I'll remove this and go back up here. So the last things we have to do here is we have to keep track of work. We want to do something with work. And sort of a generic way to do this is every time you have a comparison, right, we'll consider that a certain amount of work. You could do this a lot of different ways. This is rather unscientific, but it does give you an idea of how much work is taking place, right? So work, I'm going to add 1 to work right before I do a comparison. Okay, so I'm going to put it right here because the very next line of code is a comparison. So anytime we hit this code, we know we're going to hit this code next. So this is going to be my comparison. I'm going to increment 1 for the comparison. All right. Then, anytime we have a swap, I'm also going to add 1. All right. So here, work plus 1 for the comparison. And then here, this is for the swap. Now, swap is a relatively simple function, right? You could say that the swap might take 2 or 3 units of work, right? There's a number of different ways you could do this. If swap was another function that was 100 lines, you might make that 100 units of work, right? Again, it's rather unscientific, but it does give you an idea of how much work it takes for a given size set of data. All right, so that gives us the work. Let's run this again. Okay, so the list of length 5 required 17 units of work to sort. Now this is specific to this list because some lists you're going to need to swap more, right? Can you think of a list where that has more swaps or a list that doesn't have any swaps? So for example, if our list is already sorted, there's not going to be any swaps, right? So automatically the amount of quote-unquote work done is going to be smaller for that list, even though it could be the same size. It could be a list of 5 elements. If the list is already sorted, there will be no swaps, so the work will be less. And then if the list is completely reversed, then there's every single comparison is going to be wrong, and so every single comparison is going to be a swap, right? So if the largest item is down here, so this is 99, 88, 77, 66, 55, right? 99 and 88, they have to swap, and eventually the 99 will come all the way to the top. But then that leaves 88 over here, right? So every single one would be a swap. So depending on the data, the different types of data, the way the data is originally organized will change the actual amount of work that takes place. So when we talk about big O, we're talking about usually worst case, or average case. But generally, worst case is the most important in computer science. Worst and average cases you talk about a lot in computer science. Best case doesn't really matter that much. All right, so the worst case is what we're looking for here. And one of the clues that tells us what the time complexity of this particular algorithm is that we have two nested loops. And each one of these loops has a factor of n in it. Okay, n is the length of our data, the number of elements in our list, length of sorted, that is n. So because this loop runs n times, even though it's n minus 1, in big O notation, we don't care about the terms that aren't the most dominant, right? We only care about the dominant terms. So this term of n is dominant, multiplied by this term, which still is n. So this is essentially n times n. And if you would write this out, right, this could be n minus 1, and you can multiply that out by, down here, let me put this in a comment, this is n minus 1, and then we would multiply by this, right, which is n minus 1 minus I. But I changes depending on this, right? But either way, this winds up multiplying out to n squared. Okay? The main way you can tell is you have two loops that run, they have a term of n in them. Alright? So we're going to say that this is time complexity of n squared, which is not very good for a sorting algorithm, but this is a nice easy sorting algorithm to get started with. Alright? So that gives us our time complexity and the amount of work it took. And we can run this one more time. We see the sort succeeded, big O of n squared. And we can try a really big list too. Let's try okay. And we'll run that. Sort succeeded. 16 items in the list, 155 units of work. Okay, time complexity of this sort is big O of n squared. That basically means it took less than n squared, right? And if we look at our units of work, that's true. We weren't particularly scientific with our units of work, though. So, all right. So that is bubble sort, and we'll look at another sorting algorithm next.